In this video, we're going to discuss how to apply exponential models to word problems. So I have a summary of what we have learned in the past video of mine, that if you're modeling an exponential equation, we can take this format for it, where b is going to represent the common ratio that we find. P is going to represent the change in x's for this common ratio b. C will be represented as horizontal asymptote, and this horizontal asymptote in most cases will be 0, and that is definitely true if the ratios that we were finding to find this b were constant ratios right away on the first output values without you doing first differences on the output values first. And then in general, y-intercept is always going to be a plus c. How come? Because if you plug in 0, y-intercept is always when you put x as 0. So put 0 over here. You'll have b to the 0. b to 0 will be just 1. So you'll have a times 1 plus c, which is just a plus c. And so if you take this general equation and isolate for what a is, it's going to be a subtraction between y-intercept and c. And keep in mind that if we happen to have horizontal asymptote of 0, then this subtraction would not be there. So a will be actually the y-intercept itself, and y-intercept usually is referred to as the initial value in questions. And again, this only happens if the ratios are constant without us doing first differences first. So this might mean nothing to you if you did not watch my previous video, but as I go over this, I hope this will make sense. So let's start off by saying the let statements and reading the question. So let's start by reading. We have school's initiative for bullying is reducing incidents at around 5% every 20 days. Suppose there were 200 incidents initially. Develop a model that will represent the situation, then use it to find out when will the number of incidents be 10% of initial number of incidents. So in terms of let statements, we're going to have x to be independent variable for how many days have passed. And y is going to represent number of incidents being reported. So we have initially, so let's say at time 0, we have 200. And then we have 2% that we're trying to reduce by, not 2%, 5%, we're reducing by 5% of this 200. So 5% written as a decimal is 0.05. Multiply that with 200, you'll have 10. This is a reduction of 10 incidents within 20 days. That's the goal. So that would be 190. Then, to find the next number, you do 5% of the current 190. So 5% of 190 gives you 9.5. And so subtract that 9.5 from the 190, we have this new output value. So it's kind of tedious to do multiplication and then subtraction. So now that we have 3 output values, let's take a look to see what our ratios will be. So if we take this next one and divide it by the previous, we get 0.95. If we take this next one and divide it by the previous, we'll also get 0.95. So now we can use this ratio to actually think, okay, if we already have this number, we want to multiply it by 0.95 to find our next value in the table. And so doing so gives us this result. The x's are just going up by 20 days each time. So there's definitely a pattern there. So, because we have found our ratios to be 0.95, we can write that down as our b. Our differences in x's are going up by 20, so that could be our p in the equation. Please note that this 0.95 actually still relates to the 5% loss. It's 1 subtract 5%, but written as a decimal. And because the ratios were the same right away without us doing first differences first, the horizontal asymptote here will be 0, so c will be 0. And the first number that we see will be actually our a itself. So we have all of the numbers to create our model. Here's the model. A is 200, base is 0.95, x over 20 to represent 20 days. It takes 20 days to lose 5%. And then there's nothing added at the end, so you could say plus 0 or not write it at all. And you can check that this model actually makes sense if you use a point, this last one, to verify that the left side does indeed equals the right side. So we're not finished. Once we created the model, then there's another part to this question. We want to use this model to find out when will the number of incidents be 10% of initial number. So when do we get an output of just 20? So how did I find this 20? Well, 10% of 200, which is the initial number of incidents, is going to be 200 multiplied by 0.1, which is 20. Because we have now the model to follow, all we have to do is plug in 20 into this model. And in this model, we have a single variable x left over for which we need to solve for. So in order to solve exponential equations, we went over how to do them, but this is a quick recap how we do this. We take the numbers that have the same exponents and we can divide them out together. So we have 20 with exponent 1, this 200 is with exponent 1. So we can divide both sides by 200 so that we can isolate this base. So on this side we'll get 0.1, and this base we don't touch it. And then we're going to do something called the trial and error. In grade 12, you will learn how to use logarithms to help you do this. But for now, let's talk about how to do it with the trial and error method that we've been practicing. So what you want to do, so I got rid of my check here so I have more space. What our goal is to find an exponent on 0.95 that yields very close to this 0.1 of our result. So we're going to just try several numbers. Use a calculator, so try maybe an exponent of 2. When you do that, you get 0.9. That's too big in comparison to 0.1, which is our goal. So let's change the exponent to be higher. Why should we try numbers that are bigger than 2? Because this base is smaller than 1, so there's a decay happening. So as we increase the input, we're going to get closer to this 0.1, which is smaller than this. So let's increase the input. If we have 10, we have 0.6, which is closer, but that's not yet what we want. So let's jump to maybe an exponent of 40. When you do that, you get 0.13, which is close to 0.1. But maybe you might think, well, that's still not close enough. So you could try a few more numbers. I tried 45 as an exponent, and this gave me 0.099. And if you round that, that will be the 0.1. And I think that's pretty close, good enough for us. So once you have found a number for the exponent that works, please keep in mind that our original exponent wasn't just x, it was x over 20. So here's what I would suggest you do. You take your 0.1 and rewrite it with this expression that we found. So remember this 0.1 right here, which is close here, is equivalent to this. So just change it to be with the same base, because we're technically trying to match the bases so that we can solve for the exponent. So if the bases now match, we can now ignore the base and say this exponent 45 is equal to x over 20. And this is easily solved by x by multiplying both sides by 20 to get 900. And so then you can do your therefore statement. In 900 days, incidence will be 10% of the initial being reported. Let's do another example. I'm keeping this information here on the side as we do this one. A certain virus spreads at a rate of 15%. So now this is a virus spreading, meaning we're going to have growth instead of decay like the previous question. So it says 15% every 2 weeks. If 10 people were infected originally, what is the model for this infectious disease? Use the model to find out the annual rate of increase of infections. So we're going to concentrate on the model part first. So in our last example, we had a decrease, percent of decrease, and we said that the common ratio related to the percent rate by doing 1 minus the 5%. So then the base was 0.95. So our goal is to figure out what will happen for percent increase. What should we place over here as a relationship between the rate and the actual base ratio or common ratio number. So let's start it off, and then we'll fill this in a moment. So we're going to have two let statements. Without the let statements, your models will be ambiguous, so please include let statements or you will not get full marks. X will be independent variable, and it talks about weeks here, so we'll say number of weeks. And let Y be the dependent variable, number of people infected. Start by creating a few values in the table. We're told 10 people infected originally, so at times 0, there's 10. Then we want to find out 15% of 10. So 0.15 is changing the 15% into a decimal. Multiplying that by 10 gives us 1.5. Because it is a spread, we're going to increase by this amount. So we're going to add this amount to the 10 that we had originally. So now we have 11.5. Then we're going to do 15% of this 11.5. We get this new number. This new number has to be added to 11.5 to give us the next result. Just like we did before, we have two calculations here. We have multiplication to find the increase, and then we have to add to the original. So we multiply, then add, multiply, then add. Now that we have three outputs, however, we could say, let's find the ratios right now, because it's an exponential unit, it's supposed to be exponential. If they're consistent right away, then we can maybe find the next output using the ratio instead. So to find ratios, remember it's the next one divided by the previous, and it will give us 1.15. This next one divided by this previous will also give us 1.15. So this is a common ratio. We can apply it onto the next one and say this number multiplied by 1.15 is going to yield this result. So our ratio then is 1.15. We're going to place that as the b in our model. Our p in the model, so the divisor of the exponent, is going to be changed in x values. So here x values go up by 2, up by 2, up by 2. Could say it's 2. Please note now that we have increase, the base is supposed to be base of exponential is supposed to be bigger than 1. So it is bigger than 1, and it's specifically 1 plus 15%. So this 1 plus rate is what we can fill in over here as a summary that we can keep adding to as we go through the different word problems. Then, because our first ratios were found automatically here without us doing first differences on the outputs, then horizontal asymptote is non-existent, it's 0. Oh, it is existing, but it's at 0, sorry. And our A is going to be the y-intercept or initial value that we start with, so for us is 10. And so we have all of our numbers for our model. All you have to do is place them in here. So A is 10, base is 1.15, x over p, and then we don't need this plus 0. You could do the checking on your own. It does work out. And then our next part. We want to use the model to find out the annual rate of increase of infections. So the 15% is not annual rate. It was the biweekly rate. Watch how it's written. A rate of 15% every 2 weeks. So this 15% is only for every 2 weeks. What we want to find is the annual rate. To do so, we're going to substitute what is 1 year worth in weeks. There's 52 weeks worth weeks in a year. And so using this equation, plugging in 52 into the x, 52 divided by 2 is 26. Making sure that you don't multiply before you do the exponent. By BEDMAS, we have to apply the exponent first. So do that on the calculator and then multiply by 10. You get this result for the output. Then, in order to find the annual rate of increase, we want to find the ratio between new and the old, kind of like what we were doing here. next one divided by previous, except we're going to jump a full year into the future and take that full year into the future output and divide it by the original, which is the 10. So this is the, in a full year, this is how many infected, divided by the original, which is 10. We get the ratio that corresponds to annual increase in X values. So it would be a full year up in the future. The new ratio would be this. So how do we find a rate out of the ratio? Please remember what we just wrote up here. B is equal to 1 plus rate. And so because we know our B, we can subtract both from both sides 1 to get our rate. But please remember that this rate is the decimal version. If you want the percent version, it's actually 3,686%. So that kind of makes sense. If 15%, that's a huge percent to begin with, and that happens every 2 weeks, we're going to have a big annual rate. So that would be your therefore statement. Annual increase of infections is this big percent. Let's try another. Radioactive substance was found in a cave. It was measured to have 10 kilogram mass. The substance is known to have a half-life of 1200 years. How much of it will there be 1,000 years from now? So we're going to start adding to our summary here. We want to know what B will have to be for half-life, and maybe another question. We'll talk about what is it going to be for doubling as well. If we do that question, I'm not sure. Maybe in class we will for sure. So let's start with the let statements. Let X be number of years, because we have here time to do with years, so use that. And let Y be the mass in kilograms of this substance that is left over. Create a table. At the beginning, we're told that there's 10 kilograms of mass, so that's your initial value here. Then, we're also told that the half-life is 1200 years. So you put 1200 here. So in 1200 years, this becomes half. That's what this means, half-life. So the 10 kilograms, half of 10 is 5. Which means in another half-life, so if 2400 years have passed by, then this 5 kilograms loses half of its mass, and it's 2.5 kilograms now. So you can obviously that the ratios here will be times 0.5 times 0.5, or divide by 2, divide by 2. So the next number down will be 1.25 in 3600 years. So the ratio from this explanation is going to be the 0.5, and the differences in x's here, they go up by 1200. So that would be the p that will go into our exponential. And so we can summarize that for half-life, anytime you see a word problem and it talks about half-life, you can't automatically use b as half. And if you see words like doubling, use b as 2. If you see words like tripling, then use b equals 3, because that would be your ratio. And continuing on, the horizontal asymptote will be 0 here. Most questions will have that. And a will be our initial value. So, and a is our initial value only because the horizontal asymptote is 0. So don't always assume that that would be the case. We'll do another video with examples where that's not the case. So now that we have all the letters, you can create your model. And then we're going to not forget to check with a point. I'll skip that. Lastly, we're going to find out how much of the substance will there be 1,000 years from now. So we're going to plug in. I lost one here. Let me fix. So we want the amount in 1,000 years. So I fixed my error here. The disappearing one is there now. You're plugging in 1,000 into the x. Make sure you follow BEDMAS, so do the exponent first. you will get a repeating decimal there. So please try to use all those decimals, or actually try to enter everything into the calculator as shown with brackets. And here, make sure you do exponent next before you do multiplication by 10. And then in the end, you can do the rounding. So don't round in the intermediate steps. So we have 5.6, and then you can use a therefore statement. You should say, in 1,000 years, there will be 5.6 kilograms of this radioactive substance. So here's a note that we'll have in our when we discuss this at school. But we have the formula here that's commonly used is the one without the plus c. So as I said, usually you won't have them. So and in here I've summarized that x represents the independent variable, which is usually time. Y is final value of the dependent variable. A is the initial value of the dependent variable, except, I should say, caveat, if there is a plus c, that this statement right here is not true. Because if you have shift up and down, then it changes your initial value as well. So in general, please note this relationship that we've talked about already, that the y-intercept is going to be a plus c, and so if you rearrange what a will be, it's not going to be just your initial value, because it's going to change by the horizontal asymptote value as well. And then the b represents growth or decay factor, and you can look for special words in the question to find out what that b will have to be. So if you see the word doubling, you can use 2. If you see half-life, you can use 0.5. If you are given a percent and you're told it's increasing, you're going to do 1 plus that percent changed into a decimal. If you see percent decrease, you do 1 subtract r, that r changed into a decimal. And then the p, the denominator of the exponent, would be how long it takes for that a initial value to grow or decay by the factor b that we've discussed. So what I want to do right now is quickly recap the words factor versus rate. They're not the same things. So we're going to be using these two formulas to discuss that. And I have two questions here. We have one with a base bigger than 1, and another example with a base smaller than 1. So let's start with the function f at x. We're told that the base here is 1.9. Because it's bigger than 1, it's a growth. And we call it a growth factor because the b itself is the factor. It's not the rate yet. To find the percent rate of increase, because it's a growth, we're going to use 1 plus r to solve for the r. So 1 plus r is equal to 1.9. Subtract 1 from both sides gives us r is 0.9. Change the decimal into a percentage, you get 90% growth rate. So factor and rate, not the same things. So factor is the actual base itself. The rate is how did it change from the existing amount, which is represented by this 1. And because it went higher than 1 by 0.9, that means there's 90% as growth rate. Let's do this particular one here. In function g, the base is 0.45. It is a smaller base than 1. We have a decay. We still call it the factor. It's not the rate yet. Because it is decay, you're going to make that equivalent to 1 minus r instead and solve this equation for the rate r. So what you can do is add r to both sides to make it positive on that side and subtract 0.45 on the other side. So basically reorganize it, and solving for r gives us 0.55 as a decimal or 55% decay rate. Again, factor and decay, they're related to each other, but they're not the same. Think about it this way. You're looking at it as a comparison to 1. So this base is not 1, but it's smaller from 1 by 0.55. So the 0.55 is a loss, and this 0.45 is how much of whatever you're measuring is left over. So let's do one more note here I didn't read. We'll do an example that actually demonstrates this. Note, it says, always set up the equation with two variables, x and y, make sure you have let statements, what they represent, and then after the setup is done, use the more information provided in the question to solve it. Sometimes students use all the numbers provided right away, and they get confused where to put what the number, where the numbers go. So let's demonstrate that with an example. A drug's mass in the bloodstream decreases as time passes. So let's say you took Tylenol or something for a headache. Each hour, the 250 milligram drug loses 5% of its effectiveness. So basically there's less milligrams left in the bloodstream. What is the mass of the drug after 150 minutes? And then there's another question, how long will it take for the dose to reach a low level of 52 milligrams? So what I would suggest, the numbers inside the question, so I put brackets around these two questions, don't look at those numbers in questions until the equation is fully set up. So let's look at everything in front of that. We have each hour, so that's actually a number right here, that's 1, okay? And it talks about hours, and I know in the question it talks about minutes. We'll do the conversion later, okay? So we have hours, so let x be number of hours. It is not wrong to do it in minutes, but we'll just go with hours because that's what I set it up as. And let y be the amount of drug that's left in the bloodstream in milligrams. So as I said, each hour represents how long, so that's your p, which is just 1. This right here represents your initial amount, so 250, you can place that as A. The loss of 5% is going to relate to your base, so do not put 0.05 as the B itself. It's 1, subtract this rate. And then you put that into the equation. There is no plus C here because most of the questions will not have horizontal asymptote other than the 0 itself. So when we have this A and B filled in, we can simplify it, of course. But here is my note. The confusion sometimes comes in, where do I put what? So in the exponent, the x and the p, they both have something to do with time. And then the output over here is the final amount, and this is usually the initial amount. So both of these will be in terms of milligrams. So let's continue on with the actual question. First question was, what is the mass in 150 minutes? So because this is talking about minutes, it's something to do with the input x, because I know this is in hours, but that's a quick conversion. We take 150 divided by 60 to get how many hours is this. It's going to be 2.5 hours. And then with our model, we can plug in this 2.5 into the x, and we can follow BEDMAS. So do the exponent first before you multiply. Don't round anything in the middle, just round at the very end. And this is how many milligrams we'll have in 2.5 hours. Then we have a second question. How long will it take for the dose to reach 52 milligrams? So in here, we want to substitute the output 52. As I said here, this is in milligrams. So you watch your let statements, just follow what it says here. Put 52 out here. For us to solve for the x, because x is an exponent, you have to follow matching bases or trial and error that we've been learning. So before we do that, we need this base isolated. So we're going to divide both sides by 250. That gives us this. And the bases are not identical yet, so we're going to do some trial and error on the side. So our goal is to get this number to be the same base as the one that has the variable x. So we'll have 0.95 as something. We don't know what that something is. We want it to be as close as possible to this decimal. So we can try 2. So when we do that, we get 0.9. That's too big. We want 0.2, so we want it smaller. So I tried 10, I tried 30, I tried 31, and 31 got really close. And in my opinion, that's close enough. So we can say then, using this right here, because it is close to our 0.208, we can rewrite this version with the 0.95 base to the power of 31. And the equal sign I put now with a little dot over top to indicate it's not perfect, but it's close enough for us. Now we can ignore the base because they're identical and say the exponent 31 has to equal to that exponent, which is x.